Tonight, we're going to explore the largest empty region of space ever discovered. A void so massive that it challenges everything we thought we understood about how the universe is structured. And the truly unsettling part isn't just that this void exists, it's that we're inside it, floating in a bubble of cosmic emptiness that stretches for billions of light years in every direction. By the end of tonight, you're going to understand how this discovery changed everything we thought we knew about our place in the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Picture the universe as a vast cosmic web, not a smooth, uniform distribution of galaxies scattered randomly through space, but an intricate structure of filaments and walls surrounding enormous voids. This is what astronomers discovered in the late 20th century when they started mapping the three-dimensional positions of thousands of galaxies. The pattern that emerged was stunning. Galaxies aren't spread evenly through space like stars on a flag or dots on paper. They cluster along threads and sheets that wrap around vast empty regions. These voids, regions where very few galaxies exist, can be hundreds of millions of light years across. Between them, galaxies congregate in dense filaments and walls, creating a structure that looks remarkably like soap bubbles or the foam in your coffee. Each bubble represents a void, an enormous region of space that's nearly empty. The surfaces where bubbles meet are where galaxies cluster. This cosmic web structure is thought to result from how the universe evolved. In the very early universe, shortly after the Big Bang, tiny fluctuations existed in the density of matter. Some regions were slightly denser than average, others slightly less dense. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to their denser neighbors, becoming voids. The result is what we see today, a universe with structure on the largest scales imaginable. Computer simulations of cosmic evolution reproduce this web structure beautifully. Start with the conditions that existed shortly after the Big Bang. Let gravity do its work for 13.8 billion simulated years, and you get filaments and voids that match observations. These simulations show that the cosmic web isn't made primarily of visible matter. It's dominated by dark matter, the mysterious substance that makes up about 85% of all matter in the universe. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. We only know it exists because of its gravitational effects. The dark matter forms the scaffolding of the cosmic web. Visible matter, the stuff that makes up stars and galaxies and planets, and us, falls into this scaffolding, collecting in the densest regions. So when we look at the cosmic web, we're seeing the visible tip of a much larger dark matter structure. The galaxies are like lights on a Christmas tree. The tree itself, the underlying framework holding everything together, is made of dark matter. Now, within this cosmic web, voids come in different sizes. Small voids might be 30 or 40 million light years across. Larger voids can reach 100 or 200 million light years. These are regions where galaxy density drops dramatically compared to the filaments surrounding them. Not completely empty, a few isolated galaxies drift through these voids, but sparse. For context, the average distance between galaxies in a dense filament might be a few million light years. In a void, galaxies might be separated by tens or hundreds of millions of light years. The largest known voids in the universe include structures like the Boötes void, discovered in 1987. This void is roughly 330 million light-years in diameter. When it was first discovered, astronomers found only 60 galaxies in a region where they'd expect to find 10,000 based on average cosmic density. It looked like a hole in space, a region where galaxies simply didn't exist. The Boötes void earned the nickname the Great Nothing because of how empty it appeared. Then there's the Eridanus supervoid, a region about 1 billion light-years across. This void is associated with the CMB cold spot, a particularly cold region in the cosmic microwave background radiation. Some astronomers think the supervoid's unusual size might explain why this cold spot exists, though that's still debated. These voids are enormous, incomprehensibly vast regions of near emptiness, but they fit within our understanding of cosmic structure. They're extreme examples, sure, but they're consistent with the cosmic web model. Computer simulations predict that voids of this size should exist. We see them, and while they're remarkable, they don't break our cosmological models. And then there's the KBC void, named after researchers Keenan, Barger, and Cowie, who first identified it in 2013. The KBC void is different from all other known voids, not just in degree, but potentially in kind. The KBC void appears to be roughly 2 billion light-years across. That's about 6 times the diameter of the Boötes void. And we're not observing it from outside, looking at a distant, empty region of space. We're inside it. The Milky Way, our home galaxy, sits roughly near the center of this enormous underdense region. Let me be clear about what this means. When you look up at the night sky, the galaxies you can see, even with powerful telescopes, are mostly within this void. The nearest large clusters of galaxies, like the Virgo cluster or the Coma cluster, are at the edges of this void. We're surrounded by a region of space where galaxy density is lower than the cosmic average. Not just slightly lower, significantly lower. Studies suggest that within the KBC void, galaxy density is about 50% of what it should be, based on the average density of the universe. Imagine living in a city where half the buildings are missing, not concentrated in one neighborhood, but spread throughout the entire metropolitan area. Everywhere you look, you'd notice something was off. The density would feel wrong. That's the situation with the KBC void. Everywhere we look, out to distances of about 1 billion light-years, we find fewer galaxies than we should. The evidence for the KBC void comes from galaxy surveys. These are systematic observations that measure the positions and distances of thousands or millions of galaxies. By plotting these galaxies in three-dimensional space, astronomers can see how they're distributed. And when they do this for our local region of the universe, they see a clear pattern. Galaxy density increases as you move away from our position. At distances of about 1 billion to 1.5 billion light-years from Earth, we reach the edge of the underdense region. Beyond that, galaxy density jumps to normal cosmic values. We're in a bubble, and that bubble has a fairly sharp boundary. This is unusual. Most cosmic voids have gradual edges, regions where density slowly increases as you move from the void's center towards surrounding filaments. The KBC void appears to have a more defined boundary, which makes it stand out even more. Now, you might think, well, we're just in an unusually empty part of space. That's interesting, but why is it terrifying? The answer lies in what this means for our cosmological models and our measurements of the universe's expansion. One of the biggest challenges in modern cosmology is something called the Hubble tension. This is a discrepancy between different measurements of how fast the universe is expanding. The Hubble constant, named after astronomer Edwin Hubble, describes the rate at which distant galaxies are receding from us due to cosmic expansion. It's measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So if a galaxy is 1 megaparsec away, and the Hubble constant is 70, that galaxy is moving away from us at 70 kilometers per second due to cosmic expansion. If a galaxy is 2 megaparsecs away, it's moving at 140 kilometers per second, and so on. The problem is that different methods of measuring the Hubble constant give different results. Measurements based on observations of distant supernovae and Cepheid variable stars, stars whose brightness varies in predictable ways, give a Hubble constant of about 73 kilometers per second per megaparsec. But measurements based on the cosmic microwave background, the afterglow of the Big Bang, give a value of about 67 kilometers per second per megaparsec. That's a discrepancy of about 9%. That might not sound like much, but in cosmology, it's huge. Both measurements are done with incredible precision. The error bars on each measurement are small. This isn't just noise or measurement uncertainty, it's a real, persistent difference that refuses to go away no matter how carefully we measure. Astronomers have been trying to explain this discrepancy for years. Maybe there's something wrong with one of the measurement methods. Maybe our understanding of how Cepheid variables work is slightly off. Maybe there's systematic error we haven't accounted for. Or maybe, and this is where the KBC void becomes relevant, maybe we're getting different results because we're measuring from inside an enormous underdense region. Here's the logic. The cosmic microwave background measurements give us the expansion rate of the universe as a whole, averaged over all of space. They're telling us what the Hubble constant should be based on the universe's overall properties, its age, its composition, its density. But measurements from supernovae and Cepheids are local. They measure the expansion rate in our cosmic neighborhood out to a few 100 million light-years. If we're sitting in a void, a region where matter density is lower than average, the expansion rate we measure locally might differ from the universe's overall average expansion rate. Lower matter density means weaker gravitational pull. Weaker gravitational pull means less resistance to expansion. So within a void, space might expand slightly faster than the cosmic average. This is a testable hypothesis. If the KBC void is real and large enough, it could explain at least part of the Hubble tension. We'd measure a higher expansion rate locally because we're in an underdense region, while the cosmic microwave background gives us the true average for the whole universe. Some studies support this idea. Models that include a void roughly the size of the KBC void can reduce the Hubble tension, bringing the two measurements closer together. Not eliminating it entirely, but making it less severe. Other studies are more skeptical. They argue that even a void 2 billion light-years across isn't large enough to create the observed discrepancy. You'd need an even larger underdensity, or you'd need the void's density contrast to be more extreme than observations suggest. The debate continues. But here's what makes this truly unsettling. If the KBC void is the explanation for the Hubble tension, it means we've been systematically wrong about the expansion rate of the universe. Not wrong in the sense that our measurements are bad, but wrong in the sense that we've been measuring something that's not representative of the universe as a whole. It's like trying to determine the average temperature of Earth by only taking measurements in Alaska. Your measurements might be accurate for Alaska, but they don't tell you about the global average. We've been assuming that our local measurements of cosmic expansion are representative of the whole universe. If we're in a giant void, that assumption is violated. And this has consequences for everything built on measurements of the Hubble constant. Estimates of the universe's age depend on the Hubble constant. Estimates of how far away distant galaxies are depend on it. Our understanding of dark energy, the mysterious force driving cosmic expansion to accelerate, depends on accurate measurements of expansion rate. If our local measurements are skewed by the void we're sitting in, we need to recalibrate everything. But there's an even deeper concern. The existence of a void as large as the KBC void challenges our cosmological principle. This is the assumption, a foundational assumption in modern cosmology, that the universe is homogeneous and isotropic on large scales. Homogeneous means the universe has the same average density everywhere. Pick any large enough volume of space, measure its average density, and you'll get the same result no matter where you are. Isotropic means the universe looks the same in every direction. There's no preferred direction in space, no cosmic up or down or north or south. These assumptions are powerful because they simplify the equations of general relativity, Einstein's theory of gravity, and space-time. If the universe is homogeneous and isotropic, we can use simplified models to describe its evolution. We can talk about the universe's expansion as a whole, about its age, about its fate, without having to account for every local variation. The cosmological principle says that while the universe looks lumpy on small scales, with galaxies and clusters and voids, when you average over large enough regions, those lumpiness smooths out. Zoom out far enough, and the universe looks uniform. But what's large enough? The generally accepted scale is a few 100 million light-years. Average over regions larger than that, and the universe should look homogeneous. A void 2 billion light-years across challenges this. That's not a small-scale fluctuation that averages out. That's a large-scale structure that affects our measurements of cosmic properties. If voids this large are common, if there are many KBC-sized voids scattered throughout the universe, then the cosmological principle might not hold on the scales we thought it did. We might need to average over even larger regions, billions of light-years or more, to see true homogeneity. And if that's the case, many of our cosmological calculations become significantly more complicated. We can't use the simple models anymore. We need to account for large-scale structure when calculating expansion rates, when estimating distances, when predicting the universe's future evolution. Some cosmologists argue that the KBC void isn't actually that unusual. They point out that when you do large-scale surveys, you occasionally find regions that are underdense or overdense just by chance. Statistics says that if you sample enough regions, you'll find outliers. Maybe we just happen to live in an outlier region. That's possible. It's not impossible that we're in a 2 sigma or 3 sigma fluctuation, a region that's unusually empty but still consistent with random chance. But others argue that a void this large shouldn't exist based on our standard cosmological model. Computer simulations of cosmic structure formation don't typically produce voids quite this big with quite this sharp a boundary. They produce voids, sure, plenty of them, but generally smaller and with more gradual edges. Finding a void, like the KBC void in simulations, is rare. Not impossible, but uncommon enough that it raises questions. If observations show we're in a very rare structure, we need to ask why. Are we just lucky or unlucky, depending on how you look at it, to be in such an unusual location? Or is there something wrong with our models that makes them underpredict the size and frequency of large voids? This is where things get philosophically interesting and a bit uncomfortable. There's a concept in cosmology called the Copernican principle. This is the idea that we don't occupy a special place in the universe. Earth isn't the center of the solar system. That was Copernicus's great insight that overturned centuries of geocentric thinking. The sun isn't at the center of the galaxy. We orbit about 26,000 light-years from the galactic center. The Milky Way isn't at the center of the universe. We're just one galaxy among hundreds of billions. The Copernican principle says that when we observe the universe, we should assume we're observing from a typical location. Not the center, not an edge, not anywhere special, just a random, average spot. This principle guides how we interpret observations. When we measure cosmic expansion or galaxy distribution or anything else, we assume our measurements are representative of what you'd measure from most other locations in the universe. But if we're sitting near the center of a 2 billion light-year void, we're not in a typical location. We're in a fairly rare, unusual place. And that means our local measurements might not be representative. Does this violate the Copernican principle? Technically, no. The Copernican principle doesn't say we can't be in a void. It just says we're not in a cosmologically privileged position. Voids exist. They're part of cosmic structure, and some galaxies will inevitably be inside voids. The fact that we're in one doesn't mean the universe was designed with us at its center or anything like that. It's just chance. But it does mean we need to be more careful about extrapolating from local observations to universal conclusions. And it raises an uncomfortable question. If we're in such an unusual location, how many of our other measurements and conclusions are affected by that? How much of what we think we know about the universe is actually just what we know about our local neighborhood, skewed by the fact that our neighborhood is weird? This is the terrifying part. Not that the void exists, but that its existence undermines our confidence in measurements and models we've relied on for decades. It suggests that maybe we've been more provincial in our thinking than we realized. Maybe the universe is more complicated, more varied, more structured on large scales than our models account for. Let's talk about how astronomers actually detected the KBC void and measured its properties. This isn't easy. You can't just point a telescope at a void and see it. Voids are defined by the absence of galaxies, and you can't directly observe an absence. What you can do is map the positions of galaxies in three-dimensional space and look for regions where they're sparse. This requires two pieces of information for each galaxy: its direction on the sky, which is straightforward to measure, and its distance from us, which is much harder. Understanding how we measure cosmic distances is crucial to understanding how we discovered the void. In the early 20th century, astronomers knew very little about distances beyond our own galaxy. We knew the Milky Way was large, but we didn't know how large. We could see fuzzy spiral nebulae through telescopes, but we didn't know if they were small gas clouds within our galaxy or enormous galaxies far beyond it. The breakthrough came in the 1920s when Edwin Hubble used the Mount Wilson telescope to observe Cepheid variable stars in the Andromeda Nebula. These observations proved that Andromeda was far too distant to be part of the Milky Way. It had to be a separate galaxy entirely. Hubble's work established that the universe extends far beyond our galaxy, and that those fuzzy spiral nebulae were actually other galaxies like our own. From that foundation, astronomers developed a distance ladder, a series of techniques that build on each other to measure progressively larger distances. The first rung uses parallax, the apparent shift in a star's position as Earth orbits the Sun. This works for nearby stars, out to a few hundred light-years. Beyond that, parallax shifts become too small to measure accurately. The second rung uses standard candles, objects whose intrinsic brightness is known. Cepheid variables are one type. RR Lyrae variables are another. Red giant stars can also serve as distance indicators. By identifying these objects in distant galaxies and measuring their apparent brightness, we can calculate how far away they must be. The third rung uses even brighter standard candles that can be seen at greater distances. Type Ia supernovae are the gold standard here. These stellar explosions are so bright they can be detected across billions of light years. And because they always result from a white dwarf reaching the same critical mass, they have remarkably consistent peak brightness. See a type Ia supernova, measure its peak brightness, and you can calculate the galaxy's distance. But there's a fourth rung that becomes important at very large distances where even supernovae are rare and hard to detect. At these scales, astronomers use the relationship between a galaxy's distance and its redshift. Redshift is the stretching of light waves as space expands. The farther a galaxy is, the faster space is expanding between us and that galaxy, and the more its light is stretched toward longer, redder wavelengths. By measuring a galaxy's redshift, we can estimate its distance. This technique relies on understanding how fast the universe is expanding, which brings us back to the Hubble constant. It's circular, in a way. We use the Hubble constant to estimate distances, but we also need distance measurements to determine the Hubble constant. This is why astronomers need multiple independent methods to cross-check their work. Building three-dimensional maps of the universe requires millions of these distance measurements. For each galaxy, we measure its position on the sky, its redshift, and ideally, its distance from direct methods like supernovae or Cepheids when possible. Then we plot all these galaxies in three-dimensional space. The result is a map showing how galaxies are distributed across enormous volumes. Early galaxy surveys in the 1980s and 90s used relatively small telescopes and could map only thousands of galaxies. They revealed the basic cosmic web structure, filaments, and voids. But the maps were sparse, like looking at a city map where only a few streets are drawn in. As telescopes improved and survey techniques became more sophisticated, the maps became denser and covered larger volumes. The 2-degree field Galaxy Redshift Survey in the late 1990s mapped over 200,000 galaxies. The Sloan Digital Sky Survey, which began in 2000, eventually mapped over 3 million galaxies. These surveys transformed our understanding of large-scale cosmic structure. They showed that the cosmic web extends across the entire observable universe. They revealed enormous structures like the Sloan Great Wall, a filament of galaxies stretching across 1.37 billion light-years. And they provided the data needed to identify large voids like the KBC void. When Keenan, Barger, and Cowie analyzed galaxy survey data in 2013, they focused on our local region, the volume within about 2 billion light-years of the Milky Way. They looked at how galaxy density changed with distance from our position. In a homogeneous universe, density should be constant, on average, fluctuating randomly, but not showing any systematic trends. What they found was different. density was consistently lower than the cosmic average, out to distances of about 1 billion light-years. Then, between 1 billion and 1.5 billion light-years, density began to increase. Beyond 1.5 billion light-years, density reached and exceeded the cosmic average. This is exactly the pattern you'd expect if we were near the center of a large void. Low density at the center, gradually increasing as you move toward the void's edge, and normal or high density beyond the edge, where galaxies cluster along the void's surrounding walls. They calculated that within this underdense region, galaxy density was about 50% of what it should be, based on the cosmic average. That's a significant deficit. Imagine if half the stars in our galaxy just weren't there. The Milky Way would be noticeably dimmer and less massive. The same applies to this void. It contains about half as many galaxies as a typical region of equal size. The paper that announced these findings was careful and thorough. The authors considered various alternative explanations. Maybe the underdensity was a selection effect. Perhaps their survey was missing galaxies in certain directions or at certain distances. They checked against other surveys and found consistent results. Maybe the effect was due to peculiar velocities, the motion of galaxies through space, independent of cosmic expansion. If many local galaxies happen to be moving toward or away from us, it could skew distance estimates. They accounted for this, and the underdensity remained. Maybe it was just a statistical fluke, a random fluctuation that happened to make our neighborhood appear less dense than it really is. They calculated the probability of this and found it was low, not impossible, but unlikely enough to take the results seriously. Their conclusion was that the evidence pointed to a real large-scale underdensity, a supervoid, with the Milky Way located near its center. They named it the KBC Void, after their initials Keenan, Barger, Cowie. Since that initial discovery, other researchers have analyzed the same data and additional data from newer surveys. Most studies confirm the void's existence, though estimates of its exact size vary. Some analyses suggest it's about 1.5 billion light-years across. Others argue for 2 billion light-years, or even slightly larger. The variation comes from different definitions of where the void ends. Do you define the edge as the point where density reaches 90% of the cosmic average, or where it reaches 100%, or where it starts to exceed the average? Different choices give different boundaries. There's also the question of the void's shape. Is it roughly spherical, or is it elongated in certain directions? Some studies suggest it might be slightly ellipsoidal, stretched along one axis. This would make sense given that cosmic structure tends to be filamentary and sheet-like rather than perfectly spherical. Regardless of these details, the core finding remains solid. We're in a significantly underdense region that extends for at least 1 billion light-years in all directions. That much is not seriously disputed. Distance measurements in astronomy are challenging. You can't just use a tape measure or fire a laser at a distant galaxy and wait for the reflection. Astronomers have developed ingenious methods over the past century, each building on the previous one. The most direct method is parallax, the same technique your brain uses to judge depth when you see with 2 eyes. As Earth orbits the Sun, our viewpoint shifts by about 300 million kilometers, or about 186 million miles, over 6 months. This creates a baseline long enough to detect tiny angular shifts in nearby stars' positions against more distant background stars. The closer a star is, the larger its parallax shift. By measuring this shift precisely, we can calculate the star's distance using simple trigonometry. This method works beautifully for stars within a few hundred light-years. The European Space Agency's Gaia satellite has measured parallax for over 1 billion stars with extraordinary precision, down to micro-arcseconds for the brightest stars. A micro-arcsecond is 1/1,000,000th of an arcsecond, an angle so small that it's equivalent to measuring the width of a human hair from 1,000 kilometers away. This level of precision lets Gaia measure distances to stars thousands of light-years away. But even with Gaia's incredible capabilities, parallax only works for stars within our own galaxy and nearby dwarf galaxies. For more distant objects, we need different techniques. Enter Henrietta Swan Leavitt. Working at Harvard College Observatory in the early 1900s, Leavitt studied variable stars, stars whose brightness changes over time in regular patterns. She focused on a type called Cepheid variables, named after the star Delta Cephei, where the variation was first noticed. Leavitt was examining photographic plates of the Small Magellanic Cloud, a dwarf galaxy about 200,000 light-years from the Milky Way. On these plates, she could identify Cepheid variables by their characteristic brightness variations. And she noticed something remarkable. The Cepheids, that varied more slowly, taking more days to go through one cycle of bright to dim to bright, were also more luminous on average. There was a precise mathematical relationship between the period of variation and the star's intrinsic brightness. This discovery was revolutionary. It meant that by simply measuring how long a Cepheid takes to complete one cycle, you can determine how bright it actually is, its absolute luminosity. Then, by comparing that to how bright it appears from Earth, its apparent brightness, you can calculate how far away it must be. If a star appears dim, but you know it's actually very bright, it must be far away. If it appears bright, and you know it's actually very bright, it must be relatively close. The math is straightforward. Brightness decreases with the square of distance. So a star 4 times farther away appears 16 times fainter. Leavitt's discovery gave astronomers a powerful tool for measuring distances to any galaxy where Cepheids could be detected. Edwin Hubble used this method in the 1920s to measure the distance to Andromeda and several other nebulae, proving they were separate galaxies far beyond the Milky Way. This fundamentally changed our understanding of the universe's scale. Suddenly, the universe wasn't just our galaxy. It was an enormous expanse filled with countless other galaxies. But Cepheids have their limits. Even the most luminous Cepheids are only about 30,000 times brighter than our Sun. That sounds impressive, and it is, but it means they're only visible out to about 100 million light-years with current telescopes. Beyond that distance, they become too faint to detect reliably. For mapping cosmic structure on scales of billions of light-years, we need even brighter standard candles. Type Ia supernovae fit the bill perfectly. These are stellar explosions that occur when a white dwarf, the dense remnant of a sun-like star, accumulates matter from a companion star. As the white dwarf grows more massive, its core becomes denser and hotter. When it reaches about 1.4 solar masses, a critical threshold called the Chandrasekhar limit, the core suddenly reignites in a runaway thermonuclear explosion. The entire white dwarf is destroyed in a matter of seconds, releasing as much energy as the Sun will emit over its entire 10 billion-year lifetime. The explosion is so bright that for a few weeks, a single type Ia supernova can outshine an entire galaxy of hundreds of billions of stars. And because the explosion always occurs at the same critical mass, all type Ia supernovae have nearly identical peak brightness. They're standardizable candles. There are small variations. Some are slightly brighter or dimmer than others, but astronomers have figured out how to correct for these variations by studying the light curves, how brightness changes over time. Slower declining supernovae tend to be intrinsically brighter. Faster declining ones are dimmer, and this relationship is consistent enough that we can use it to standardize the measurements. With type Ia supernovae, we can measure distances across billions of light-years. These explosions are so bright they can be seen halfway across the observable universe. In the 1990s, two teams of astronomers used type Ia supernovae to discover that cosmic expansion is accelerating, driven by some mysterious dark energy. This discovery won the Nobel Prize in Physics in 2011. But type Ia supernovae have their own limitations. They're rare, occurring only about once per century per galaxy. To find them, you have to monitor thousands of galaxies and wait for a supernova to happen. Then you have to catch it at peak brightness, which lasts only a few weeks. Miss that window, and the supernova fades too much to be useful for distance measurements. This means that while supernovae are excellent for measuring distances to individual galaxies, they're not practical for mapping the positions of millions of galaxies systematically. For large-scale surveys, astronomers typically use redshift as a distance proxy. Redshift is the stretching of light as it travels through expanding space. As the universe expands, space itself stretches, and light waves traveling through that space get stretched too. The wavelengths become longer, shifting toward the red end of the spectrum. The amount of stretching depends on how long the light has been traveling, which depends on the source's distance. A galaxy twice as far away has been expanding away from us twice as long, so its light is shifted twice as much. By measuring a galaxy's redshift, which requires taking a spectrum of its light and identifying characteristic patterns of absorption or emission lines, we can estimate its distance. This technique allows astronomers to measure distances to millions of galaxies efficiently. Modern spectrographs can observe hundreds or even thousands of galaxies simultaneously, measuring redshifts for vast samples. The catch is that redshift-based distances are only as good as our knowledge of the Hubble constant, the rate of cosmic expansion. And as we've discussed, the Hubble constant is precisely what's under debate due to the Hubble tension. This creates a potential circularity. We use the Hubble constant to convert redshifts to distances, but we also need accurate distances to determine the Hubble constant. Astronomers break this circularity by using direct distance measurements from Cepheids and supernovae to calibrate the redshift distance relationship. They measure redshifts and direct distances for a sample of nearby galaxies, establish the relationship, then extrapolate to more distant galaxies where only redshift measurements are available. This works reasonably well for most purposes. But it means that if there's a systematic error in our understanding of local expansion rates, perhaps due to being in a void, that error propagates into all our redshift-based distance estimates. The discovery of the KBC void relied heavily on these distance measurement techniques. Researchers compiled data from multiple galaxy surveys, each using redshift measurements to estimate distances. They plotted galaxy positions in three-dimensional space and looked for patterns. The underdensity showed up as a systematic deficit of galaxies in our local region compared to more distant regions. To verify this wasn't just an artifact of the redshift method, some studies cross-checked using direct distance measurements from supernovae. The result was consistent. The void is real. For nearby galaxies, within a few tens of millions of light-years, Astronomers use techniques like Cepheid variables. These are stars whose brightness varies in a regular, predictable pattern, discovered to have this special distance indicating property by Henrietta Swan Leavitt in 1912. Leavitt was working as a computer, which in those days meant a person, usually a woman, who performed calculations and analyzed astronomical data. The term computer referred to the job of computing, not to machines. Women like Leavitt were employed at observatories to do the painstaking work of examining photographic plates, measuring star positions and brightness, and cataloging their findings. Despite being paid far less than their male colleagues and rarely receiving credit for their discoveries, these women made fundamental contributions to astronomy. Leavitt studied thousands of variable stars on photographic plates of the Magellanic Clouds, small companion galaxies to the Milky Way visible from the southern hemisphere. She measured the periods of variation for Cepheid variables, how many days each star took to go through one complete cycle, from bright to dim and back to bright. She also measured their average brightness on the photographic plates. The Magellanic Clouds are far enough away that all the stars in them are essentially the same distance from Earth. This was the key insight. If all the Cepheids she was studying were at the same distance, then differences in apparent brightness must reflect differences in actual luminosity. Leavitt found that the Cepheids, with longer periods, those that took more days to complete one cycle, were brighter than those with shorter periods. And the relationship wasn't random. It followed a precise mathematical pattern. Plot period against brightness on a graph, and the points fell along a smooth curve. This period luminosity relationship meant that Cepheids could serve as standard candles for distance measurement. But Leavitt didn't live to see the full impact of her discovery. She passed away in 1921 at age 53. Edwin Hubble used her work to measure distances to nearby galaxies, fundamentally changing our understanding of the cosmos. Had she lived longer, she might well have been considered for a Nobel Prize for this contribution. Cepheid variables work as distance indicators because their pulsation is driven by a well-understood physical mechanism. The outer layers of these stars undergo cycles of expansion and contraction. When the layers expand, they become less dense and more transparent, allowing more light to escape. The star brightens. When the layers contract, they become denser and more opaque, trapping light inside. The star dims. The period of pulsation depends on the star's mass and radius. More massive and larger stars pulsate more slowly. And because mass and radius are related to a star's total luminosity, the period correlates directly with brightness. Astronomers can observe a Cepheid, measure its period by watching it pulse over days or weeks, and immediately know its intrinsic luminosity. Compare that to its apparent brightness as seen from Earth, and the distance follows from the inverse square law of light. Modern telescopes can detect Cepheids in galaxies up to about 100 million light-years away. The Hubble Space Telescope, operating above Earth's atmosphere where atmospheric turbulence doesn't blur images, has been particularly valuable for Cepheid observations. Hubble's sharp vision can resolve individual stars in galaxies that appear as fuzzy smudges from ground-based telescopes. Over its 3-decade mission, Hubble has observed Cepheids in dozens of galaxies, building up a precise distance ladder. These measurements are crucial for calibrating the Hubble constant. By knowing the exact distances to nearby galaxies and measuring their recession velocities, astronomers can determine how fast the universe is expanding at our location. But Cepheids only get us so far. Beyond 100 million light-years, even Hubble can't reliably detect them. We need something brighter. For more distant galaxies, Astronomers use type Ia supernovae. These are stellar explosions that occur when a white dwarf star, the remnant of a sun-like star, after it has exhausted its nuclear fuel, accumulates matter from a companion star until it reaches a critical mass. Understanding how type Ia supernovae work requires understanding stellar evolution and what happens to stars like our Sun. Our Sun is currently in a stable phase called the main sequence, where it fuses hydrogen into helium in its core. This has been going on for about 4.6 billion years and will continue for another 5 billion years or so. Eventually, the Sun will exhaust the hydrogen in its core. When that happens, the core will contract and heat up while the outer layers expand enormously. The Sun will become a red giant, growing to perhaps 100 times its current diameter, possibly swallowing Mercury and Venus and making Earth uninhabitable. After the red giant phase, which lasts a few 100 million years, the Sun will shed its outer layers in a planetary nebula. What remains is the core, a hot, dense object about the size of Earth, but containing about 60% of the Sun's original mass. This is a white dwarf. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. They're held up against gravitational collapse, not by nuclear fusion, which has stopped, but by quantum mechanical pressure called electron degeneracy pressure. Electrons resist being squeezed too close together, and at white dwarf densities, this resistance is strong enough to balance gravity. A white dwarf, left alone, will simply cool off over billions of years, eventually becoming a cold, dark cinder. But if a white dwarf is in a binary system with a companion star, things can get more interesting. If the companion is a red giant or another evolved star with loose outer layers, matter can flow from the companion onto the white dwarf. This accretion adds mass to the white dwarf over thousands or millions of years. As the white dwarf gains mass, it becomes smaller and denser. This seems counterintuitive, but it's a consequence of how electron degeneracy pressure works. Adding mass compresses the white dwarf more, making it denser and smaller. There's a limit to how massive a white dwarf can be, called the Chandrasekhar limit, after Indian astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930. He showed that electron degeneracy pressure can only support a white dwarf up to about 1.4 solar masses. Beyond that mass, the pressure isn't strong enough, and the white dwarf must collapse. When an accreting white dwarf approaches this limit, something catastrophic happens. The core temperature rises to the point where carbon, which makes up much of the white dwarf, can fuse into heavier elements. Normally, this fusion would cause the core to expand and cool, regulating the reaction. But in a white dwarf, the matter is degenerate, meaning its pressure doesn't depend on temperature. So when fusion starts, there's no negative feedback to slow it down. The fusion rate increases exponentially in a runaway thermonuclear explosion. Within about 1 second, the entire white dwarf is consumed by nuclear burning. Carbon and oxygen fuse into iron group elements, releasing enormous energy. The white dwarf is completely destroyed, blown apart with nothing left behind, no remnant core, no neutron star, no black hole. The explosion ejects about 1.4 solar masses of material at speeds of 10,000 to 20,000 kilometers per second, or about 6,000 to 12,000 miles per second. That's several percent of the speed of light. The material carries away enormous kinetic energy and also emits prodigious light. At peak brightness, which occurs about 2 to 3 weeks after the explosion begins, a type Ia supernova can shine with the luminosity of 5 billion suns. That's bright enough to be visible across billions of light years. And here's the crucial point for using them as distance indicators, because the explosion always occurs at the same critical mass, the Chandrasekhar limit, type Ia. Supernovae all have nearly the same peak brightness. There are variations. The explosion physics isn't perfectly identical every time, but these variations are small and can be calibrated using the light curve shape. Astronomers discovered that brighter type Ia supernovae decline more slowly after peak, while dimmer ones fade faster. This width-luminosity relationship allows for precise standardization. Observe a type Ia supernova. Measure how its brightness changes over time. Apply the correction based on decline rate, and you know its intrinsic peak luminosity. Compare that to its observed brightness, and the distance follows. In the 1990s, two independent teams of astronomers used type Ia supernovae to measure distances to galaxies billions of light years away. Their goal was to determine whether cosmic expansion was slowing down or speeding up. According to general relativity, matter's gravity should cause expansion to decelerate over time. The question was, how much deceleration? Would it be enough to eventually reverse expansion and cause the universe to recollapse in a big crunch? Or would expansion continue forever, just slowing down asymptotically? Both teams found something shocking. The distant supernovae were dimmer than expected, meaning they were farther away than expected. The expansion of the universe wasn't decelerating, it was accelerating. Distant galaxies were receding faster than they should be if expansion was slowing down. This discovery, announced in 1998, revolutionized cosmology. It implied the existence of some form of energy, now called dark energy, that exerts a repulsive effect, pushing space apart. Dark energy makes up about 70% of the universe's total energy content, yet we have no idea what it is. The discovery earned Saul Perlmutter, Brian Schmidt, and Adam Riess the Nobel Prize in Physics in 2011. Type Ia supernovae have become the gold standard for measuring cosmic distances at scales of hundreds of millions to billions of light years. They're rare. Only about 3 type Ia supernovae occur per millennium per galaxy. But by monitoring thousands of galaxies, astronomers can find dozens per year. Modern supernova surveys scan large areas of sky repeatedly, looking for new points of light that weren't there before. When a candidate is found, rapid follow-up observations measure the light curve and spectrum to confirm it's a type Ia supernova and to gather the data needed for distance measurement. These observations have been crucial for mapping cosmic structure and for calibrating the Hubble constant. But they're limited in coverage. You can't measure supernovae in every galaxy, only in the few where a supernova happens to occur during your observation period. For comprehensive mapping of millions of galaxies, we need a different approach. Using these techniques, astronomers have built 3-dimensional maps of galaxy positions out to billions of light years. These maps reveal the cosmic web structure, the filaments and voids. And when researchers analyzed these maps for our local region, they noticed something odd. Starting from our position and extending outward, galaxy density is consistently lower than average. At first, this wasn't considered alarming. Small-scale fluctuations in density are expected. But as surveys became more complete and covered larger volumes, the pattern persisted. Out to 500 million light-years, low density. Out to 1 billion light-years, still low density. The underdense region kept getting bigger as more data came in. By 2013, when Keenan, Barger, and Cowie published their analysis, the evidence was strong enough to propose that we're in a distinct, large-scale structure, a supervoid. They estimated its size at roughly 2 billion light-years, and noted that we appear to be located near its center. Subsequent studies have refined these estimates. Some suggest the void might be slightly smaller, perhaps 1.5 billion light-years. Others argue it could be even larger, reaching 2.5 billion light-years. The exact size depends on how you define the void's boundary and which datasets you use. But the consensus is that we're definitely in a significantly underdense region, whatever its exact dimensions. One way to visualize this is to imagine plotting galaxy density as a function of distance from Earth. If we were in a typical location, you'd expect density to fluctuate randomly around the cosmic average. Some regions denser, some less dense, but averaging out to the mean. Instead, what we see is a systematic trend. Density starts low near us and gradually increases as you move outward, eventually reaching and exceeding the cosmic average at distances beyond 1 billion light-years. This isn't random fluctuation, it's a gradient, a systematic change in density with distance. That's the signature of a void. We're near its center where density is lowest, and density increases as you approach the void's edge. Now, let's address an important question. Could the KBC void be an illusion, an artifact of how we're measuring distances? This is a legitimate concern because distance measurements in astronomy have uncertainties. If we're systematically overestimating or underestimating distances to certain galaxies, we could create an apparent structure that doesn't really exist. For example, if we underestimate distances to nearby galaxies, we'd think they're closer than they are, which would make the local region appear denser than it is. If we overestimate distances to more distant galaxies, we'd spread them out in our maps, making distant regions appear less dense. The combination could create an apparent void where none exists. Astronomers have checked for this. They've used multiple independent methods to measure distances and compared results. They've looked for systematic errors in their measurements. And while there are always uncertainties, the evidence suggests the void is real. Different distance indicators, Cepheids, supernovae, and even measurements based on galaxy surface brightness all point to the same conclusion. We're in an underdense region. Another check is to look at the cosmic microwave background. This is the radiation left over from the Big Bang, a faint glow that fills all of space. It's almost perfectly uniform, with tiny temperature fluctuations of only about 1 part in 100,000. But those tiny fluctuations carry information about the structure of the early universe. When photons from the cosmic microwave background pass through voids on their way to us, they experience a small effect called the integrated Sachs-Wolf effect. As a photon enters a void, it climbs out of a gravitational potential well, losing energy and becoming slightly redder, shifting to longer wavelengths. As it exits the void, it falls back into a potential well, gaining energy and becoming slightly bluer. In a static universe, these effects would cancel out. But because the universe is expanding, and because dark energy is causing that expansion to accelerate, the potential wells evolve while the photon is crossing them. The result is a net shift in the photon's energy. Photons crossing large voids show a slight temperature decrease in the cosmic microwave background, a cold spot. Astronomers have looked for this effect associated with the KBC void. The results are intriguing, but not definitive. There does appear to be a slight temperature anomaly in the direction of the void, but it's small and near the noise level of the measurements. more sensitive future observations might clarify this. So the evidence points to the void being real, not an artifact. We're genuinely in a large underdense region. What causes voids to form in the first place? As I mentioned earlier, it comes down to the amplification of tiny density fluctuations in the early universe. Shortly after the Big Bang, the universe was almost perfectly uniform. Almost, but not quite. Quantum fluctuations during the inflationary period, the brief moment of exponential expansion in the first fraction of a second after the Big Bang, created tiny variations in density. Some regions were slightly denser, others slightly less dense. These fluctuations were tiny, only about 1 part in 100,000. But over billions of years, gravity amplified them. Denser regions attracted more matter, growing denser still. As matter flowed toward these overdense regions, it left behind underdense regions. These underdense regions became voids. The process is similar to what happens when you pour cream into coffee. At first, the cream forms distinct swirls and patterns. But, even without stirring, diffusion will eventually smooth everything out. Except in the universe, gravity does the opposite of diffusion. Instead of smoothing things out, gravity makes the lumpy parts lumpier and the empty parts emptier. The timeline of void formation is tied to the overall evolution of cosmic structure. In the very early universe, a few 100 million years after the Big Bang, structure was just beginning to form. The first stars and galaxies were appearing in the densest regions. Voids existed, but were smaller and less pronounced. By the time the universe was a few billion years old, voids had grown substantially. Galaxies had clustered along filaments, leaving large underdense regions between them. By today, 13.8 billion years after the Big Bang, the void structure is well developed. Voids like the KBC void, if it's been around for most of cosmic history, have had billions of years to evacuate matter toward their surrounding walls. One interesting aspect of voids is that they're not completely empty. Even in the KBC void, there are some galaxies. They're rare, but they exist. These void galaxies tend to have certain characteristics. They're often smaller and less massive than galaxies in denser regions. They have lower rates of star formation. They're more likely to be spiral galaxies rather than elliptical galaxies. This makes sense. In dense environments, galaxies frequently collide and merge, which tends to produce large elliptical galaxies and triggers bursts of star formation. In voids, galaxies evolve in isolation. They don't merge as often. They don't experience as many gravitational interactions, and their star formation proceeds at a gentler pace. There's even some evidence that void galaxies have different chemical compositions. Galaxies build up heavier elements over time, as stars fuse hydrogen and helium into carbon, oxygen, iron, and other elements. When massive stars explode as supernovae, they distribute these elements into space, where they get incorporated into new stars. In dense environments, this recycling happens efficiently. In voids, with fewer galaxies and less star formation, the enrichment process is slower. Void galaxies might have slightly lower abundances of heavy elements compared to galaxies in denser regions. Now, let's explore what the future might hold for studies of the KBC void and what it means for cosmology going forward. The most important need is better data. Current galaxy surveys have mapped millions of galaxies, but to really pin down the void's properties, its exact size, its density profile, the sharpness of its boundary, we need surveys that map even more galaxies over larger volumes. Several next-generation surveys are planned or underway. and they promise to revolutionize our understanding. The Dark Energy Spectroscopic Instrument, or DESI, began operations in 2021 at Kitt Peak National Observatory in Arizona. DESI is designed to measure spectra and redshifts for 35 million galaxies and quasars over 5 years. The instrument uses 5,000 robotic fiber positioners, small robotic arms that can point optical fibers at different targets in the sky. In a single observation, DESI can simultaneously measure spectra for 5,000 objects. Every 20 minutes, the robots reposition the fibers to target 5,000 new objects. Night after night, DESI scans the sky, building up a massive three-dimensional map of cosmic structure. The data from DESI will let astronomers trace the cosmic web in unprecedented detail. We'll see filaments, walls, and voids across billions of light years. We'll be able to measure how structure has evolved over cosmic time by comparing nearby regions to distant regions where we're seeing the universe as it was billions of years ago. And crucially, we'll be able to determine whether the KBC void is an isolated anomaly or one of many such structures. If DESI finds many voids of similar size scattered throughout the universe, that would suggest our models need adjustment to account for more large-scale structure. If the KBC void remains unique, that raises questions about why we're in such an unusual location. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s. This observatory features an 8.4-meter mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel camera that can photograph an area of sky 40 times larger than the full moon in a single exposure. The Rubin Observatory will conduct the Legacy Survey of Space and Time, photographing the entire visible southern sky every few nights for 10 years. It will detect billions of galaxies, thousands of supernovae, millions of asteroids, and countless other transient phenomena. For studies of cosmic structure, Rubin's deep, repeated imaging will enable photometric redshift measurements for billions of galaxies. Photometric redshifts use multicolor images rather than spectra to estimate distance. They're less precise than spectroscopic redshifts, but they can be measured for far more objects. With billions of galaxy positions mapped, we'll see cosmic structure at resolutions previously impossible. The Euclid Space Telescope, launched by the European Space Agency in 2023, is specifically designed to map the geometry of the universe and study dark energy. Euclid will observe about 1/3 of the sky, measuring shapes and redshifts for over 2 billion galaxies. Operating from space eliminates atmospheric blurring, giving Euclid exceptionally sharp images. The mission will create the most detailed three-dimensional map of the universe ever made, covering distances out to 10 billion light-years. With Euclid data, astronomers will trace how cosmic structure formed and evolved from the early universe to the present. They'll measure the clustering of galaxies with unprecedented precision. And they'll test whether large voids, like the KBC void, fit within standard cosmological models or require new physics to explain. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will complement these surveys with infrared observations. Roman will have a field of view 100 times larger than Hubble's, allowing it to conduct wide-area surveys much faster. It will hunt for supernovae, study dark energy, and map the distribution of galaxies across cosmic time. Together, these observatories will provide data that dwarfs everything we've collected so far. We're about to enter a golden age of cosmological surveys where the limiting factor won't be data availability, but rather our ability to analyze and interpret the flood of information. Computational tools are advancing to meet this challenge. Modern cosmological simulations can model billions of particles representing dark matter and gas, evolving over billions of years of cosmic time. These simulations run on some of the world's most powerful supercomputers, requiring millions of processor hours to complete. The Illustris TNG project, one of the most advanced simulation suites, models a cubic volume of space over 1 billion light-years across. It includes not just dark matter, but also normal matter, gas that can cool, condense into galaxies, form stars, and experience feedback from supernovae and black holes. The simulation produces synthetic universes that look remarkably similar to the real universe. Galaxies form along filaments, voids develop between overdense regions, and the cosmic web structure emerges naturally. By analyzing these simulations, astronomers can predict what observations should show. They can test whether voids the size of the KBC void should exist in a standard cosmological model. Current simulations suggest that, while rare, such voids are possible. But they occur in only about 1% to 5% of simulated volumes, making them uncommon, but not impossibly so. If we refine the simulations and still find that KBC-scale voids are extremely rare, that would be a problem for the standard model. It would suggest we're in a highly atypical location, which isn't forbidden, but is statistically unlikely. Alternatively, if future observations find many such voids, that would indicate our models underestimate how much structure forms on large scales. Perhaps there's more variation in initial conditions than we account for. Perhaps dark matter's properties differ slightly from our assumptions. Perhaps dark energy's influence on structure formation is more complex than current models include. These are the kinds of questions that data from upcoming surveys will help answer. Beyond just mapping structure, there's the deeper theoretical question of what the void means for our understanding of space-time and gravity. General relativity. Einstein's theory describes how matter curves space-time and how that curvature affects the motion of matter and light. In cosmology, we typically use simplified solutions to Einstein's equations that assume perfect homogeneity. The Friedmann-Lemaitre-Robertson-Walker metric, which describes an expanding universe, assumes that matter is distributed uniformly. This works well for describing the universe's overall evolution, its expansion, its age, its eventual fate. But it's an approximation. The real universe isn't perfectly homogeneous. It has structure, clusters, filaments, voids. For most calculations, we can treat this structure as small perturbations on top of the homogeneous background. Calculate the average behavior, then add corrections for local deviations. The KBC void, if it's as large as it appears, challenges this approximation. A region 2 billion light-years across, with 50% of the normal galaxy density, isn't exactly a small perturbation. It's a significant deviation from homogeneity that extends over a substantial fraction of the observable universe's radius. Some cosmologists argue that we need to account for these large-scale inhomogeneities more carefully when calculating cosmological parameters. There's a field called inhomogeneous cosmology that develops more sophisticated models, allowing for realistic structure. These models are mathematically complex and computationally expensive, which is why they're not used as standard tools. But for understanding effects like the Hubble tension, they might be necessary. If the universe's expansion rate varies from place to place due to local matter density, then averaging over those variations requires careful treatment. You can't just measure locally and assume it applies globally. Another theoretical angle involves testing modifications to general relativity. Some physicists have proposed that maybe gravity behaves differently on very large scales than Einstein's theory predicts. These modified gravity theories could explain cosmic acceleration without invoking dark energy. They might also predict different structure formation, potentially producing larger voids or different void properties. Testing these theories requires precise measurements of structure on the largest possible scales. The KBC void, sitting in our local universe, where we can study it in detail, provides an excellent laboratory for such tests. By measuring how galaxies move within and around the void, how light bends as it passes through the void's lower density regions, and how the void's structure evolved over time, we can test whether gravity behaves as Einstein predicted or requires modification. These tests are ongoing and will intensify as new data arrives. If we find many KBC-scale voids scattered throughout the universe, that would suggest our models need updating to account for more large-scale structure. If the KBC void remains unique or extremely rare, that raises its own set of questions about why we happen to be in such an unusual place. Another avenue of investigation is simulations. Modern cosmological simulations can model the evolution of structure in enormous volumes of space, tracking billions of particles representing dark matter and gas. These simulations can tell us how often voids, like the KBC void, should form in a universe governed by our current understanding of physics. If simulations consistently fail to produce voids this large, that's a sign that something in our model is missing or wrong. Maybe the properties of dark energy are slightly different than we think. Maybe dark matter behaves in ways we haven't accounted for. Maybe the initial conditions after inflation were different than our simplest models suggest. On the flip side, if simulations can produce KBC-scale voids under certain conditions, we can learn what those conditions are and test whether they match other observations. There's also the question of how the KBC void affects measurements beyond just the Hubble constant. Studies of dark energy rely on observations of how cosmic expansion changes over time. If we're in a void, and that skews our local measurements of expansion, it could affect our conclusions about dark energy's properties. Dark energy is already one of the biggest mysteries in physics. We don't know what it is. We just know it exists because cosmic expansion is accelerating. If our measurements of that acceleration are affected by our location in a void, we need to account for that before we can confidently constrain dark energy's nature. Similarly, measurements of the universe's overall matter density depend partly on observations of how galaxies cluster. If we're in an underdense region, our local measurements might underestimate the true cosmic average. These are subtle effects, and teasing them apart requires careful analysis. But they're important because so much of modern cosmology rests on precise measurements of cosmic parameters. Small systematic errors can propagate through calculations and lead to wrong conclusions. Let's consider a broader implication. If the KBC void is real and affects our measurements significantly, it means that ground-based or local observations aren't always sufficient to understand the universe as a whole. We need to think more carefully about sample bias and selection effects. This isn't a new idea in science. In many fields, researchers have to worry about whether their sample is representative of the population they're studying. In cosmology, we've generally assumed that as long as we observe large enough volumes, we're seeing a fair sample of the universe. The KBC void suggests that large might need to be even larger than we thought. We might need to observe out to several billion light-years, beyond the void's edge, to be confident we're seeing representative cosmic structure. Fortunately, this is becoming possible. Our telescopes and surveys are getting powerful enough to map the universe out to these distances. Within the next decade or two, we'll have comprehensive three-dimensional maps of galaxy positions covering enormous volumes, enough to put the KBC void in context and see whether it's truly unusual or just one example of a class of structures we hadn't properly appreciated before. There's also a positive angle to all this. The existence of the KBC void, if confirmed to be as large and significant as current evidence suggests, gives us a natural laboratory for testing cosmological models. Different models of dark energy, dark matter, and cosmic inflation make different predictions about the size and frequency of voids. By studying the KBC void in detail, by measuring its density profile, its shape, its history, we can test these predictions. If a particular model can't explain the void's existence or properties, we can rule that model out. If another model predicts exactly what we observe, that's evidence in its favor. Science progresses by confronting theories with observations. Anomalies and unexpected findings are opportunities to learn. The KBC void is exactly this kind of opportunity. It's a challenge to our current understanding, which means it's a chance to improve that understanding. Let me address one more aspect of this. Some people, when they hear that we're in a giant void, jump to the conclusion that this means we're special or that the universe was designed with Earth at its center. That's not what the science says. Being in a void doesn't make us central or privileged in any cosmic sense. Voids are a natural part of cosmic structure. They're predicted by our understanding of how gravity shapes the distribution of matter. Many voids exist throughout the universe. They're not rare, though voids as large as the KBC void appear to be uncommon. Billions of galaxies are located within voids, just as billions are located along filaments. There's nothing cosmically significant about being in a void versus being on a filament. It's just where we happen to be, determined by the initial density fluctuations in our region of the early universe. The idea that Earth or humanity occupies a special place in the cosmos is an old one that's been repeatedly overturned. Ancient civilizations placed Earth at the center of the universe because, from our perspective, everything appears to revolve around us. The sun rises and sets, the stars wheel overhead, the planets wander against the stellar background. For thousands of years, this geocentric model seemed obvious and was codified in the astronomical systems of ancient Greece, medieval Europe, and many other cultures. Copernicus challenged this in the 16th century by proposing that Earth orbits the Sun, not the other way around. His model explained planetary motions more simply than the geocentric model, though it was controversial because it displaced Earth from the cosmic center. Galileo's telescopic observations in the early 17th century supported the heliocentric model. He saw moons orbiting Jupiter, showing that not everything circles Earth. He saw phases of Venus, explained by Venus orbiting the Sun. He saw mountains and craters on the Moon, showing that celestial bodies weren't perfect spheres of quintessence, but were made of ordinary matter. These discoveries gradually shifted the consensus toward the Copernican model. Earth wasn't the center. It was one planet among several orbiting the Sun. But for a while, people still thought the Sun might be the center of the universe, with all the stars orbiting around it or fixed on a distant sphere. In the 19th and early 20th centuries, astronomers realized that stars are suns, scattered through space at various distances. The Sun isn't at any special location. It's just one star in a vast collection of stars that make up the Milky Way galaxy. Measurements of the Sun's motion showed that it orbits the galactic center, about 26,000 light-years away, completing one orbit every 230 million years. The Sun is in the outskirts of the galaxy, not near its center. We're in a suburban part of the galactic disk, far from the dense core where millions of stars crowd together. Then, as we discussed earlier, Edwin Hubble showed in the 1920s that many of the fuzzy nebulae visible through telescopes were actually other galaxies far beyond the Milky Way. The universe wasn't just our galaxy. It was filled with billions of galaxies, each containing billions of stars. The Milky Way, despite having hundreds of billions of stars, is just one galaxy among countless others. And it's not even an especially large or remarkable galaxy. It's a spiral galaxy of moderate size, similar to millions of others throughout the universe. Each step in this progression moved humanity further from any claim of cosmic centrality. We're not on the planet at the center of the universe. We're not orbiting the star at the center of the galaxy. We're not in the galaxy at the center of anything. We're on an ordinary planet, orbiting an ordinary star, in an ordinary galaxy, in what appears to be an ordinary part of the universe. This realization, sometimes called the Copernican principle or the principle of mediocrity, has become a guiding assumption in cosmology. We don't occupy a special or privileged position. Our observations should be typical of what any observer anywhere in the universe would see from their location. The discovery that we're in a large void doesn't violate this principle, but it does complicate it. If we're in an unusually empty region, then our local observations might not be representative of the universe as a whole. That doesn't make us cosmically special in any meaningful sense. It just means we need to be careful about extrapolating from local to universal. It's a practical consideration for doing accurate cosmology, not a philosophical statement about humanity's significance. To put it another way, voids have to be somewhere, and some galaxies have to be in them. The fact that we're in one is chance, not design. If the KBC void is real, and roughly the size that current evidence suggests, then about 1% of all galaxies might be within it. That's a small fraction, but with hundreds of billions of galaxies in the observable universe, 1% still means billions of galaxies share our location. We're not alone in the void. If intelligent civilizations exist elsewhere in the universe, some of them are almost certainly in voids too. They'd face the same challenges we do, measuring cosmological parameters from an underdense region, dealing with systematic effects on their observations. They might even discover their own local void and wonder about its implications, just as we're doing now. The real significance of the KBC void isn't that it makes us special, it's that it reveals how complex the universe is. It shows that even on the largest scales we can observe, structure exists. The universe isn't smooth and uniform everywhere. It has personality, variation, different regions with different properties. And that complexity is part of what makes cosmology fascinating and challenging. If the universe were perfectly uniform, cosmology would be easier but less interesting. We could make measurements locally and know they applied everywhere. But the universe isn't like that. It's structured, varied, full of surprises. The cosmic web of filaments and voids is one such surprise. The existence of enormous voids, like the KBC void, is another. Each discovery like this forces us to refine our understanding, to develop more sophisticated models, to think more carefully about what our observations are telling us. That's how science progresses. Not by confirming what we already think we know, but by encountering phenomena that challenge our assumptions and force us to dig deeper. The KBC void is exactly this kind of phenomenon. It fits within our general framework of structure formation, driven by gravity, amplifying density fluctuations. but it's pushing the boundaries of what that framework predicts. It's making us question whether our models fully capture the richness of cosmic structure. And that's valuable, because if our models have blind spots or oversimplifications, we need to know about them. We need to fix them, to make them more accurate and comprehensive. The ultimate goal of cosmology is to understand the universe as it actually is, not as we'd like it to be, or as our simplified models describe it. Reality is the final arbiter. If reality is more complex than our models, then our models need improvement. The KBC void might be pointing to exactly such a need. The fact that our location affects our measurements doesn't mean we're special. It means we need to be smart about correcting for local effects when we try to draw conclusions about the universe as a whole. Any civilization, anywhere in the universe, would face similar challenges. If they're in a dense cluster, their local measurements would be skewed toward higher density. If they're on a filament, they'd see different large-scale structure than we do. Cosmology is hard, partly because we can only observe from one location. We can't set up telescopes in other galaxies to get a different perspective. We have to do our best to account for our particular vantage point and figure out what the universe as a whole looks like, despite the limitations. Let me also note that not all astronomers agree about the significance of the KBC void. This is an active area of research with ongoing debate. Some cosmologists argue that while the void exists, it's not large enough or underdense enough to explain the Hubble tension. They point to alternative explanations for the tension, such as systematic errors in distance measurements or new physics beyond our current models. Others argue that the void is one piece of a larger puzzle. Maybe it partially explains the Hubble tension in combination with other factors. Maybe it's highlighting the fact that we need better statistical methods for analyzing galaxy surveys. Maybe it's pointing to the need for more sophisticated models that don't assume perfect homogeneity even on large scales. The scientific process involves testing ideas, comparing them to data, and refining our understanding. The KBC void is part of that process. It's a feature of the universe that we're still trying to fully understand. As with many frontiers of science, there's uncertainty and disagreement. That's normal and healthy. It drives research forward. Looking ahead, the next 10 to 20 years will be crucial for resolving questions about the KBC void. New surveys will give us much better data. New simulations will test whether our models can produce structures like this. New theoretical work will explore how voids affect various cosmological measurements. The data from DESI, Rubin, Euclid, and Roman will create the most comprehensive map of cosmic structure ever assembled. We'll see the universe in 3 dimensions with unprecedented clarity and depth. We'll trace how structure evolved from the early universe, when it was nearly uniform, to today's complex cosmic web. We'll measure the properties of thousands of voids, not just the KBC void, and understand their statistical distribution. We'll test whether large voids are rarer than models predict, confirming that the KBC void is anomalous or more common than expected, suggesting our models need revision. We'll measure the Hubble constant with multiple independent methods, cross-checking for systematic errors. We'll determine whether accounting for the KBC void resolves the Hubble tension, or whether that discrepancy has some other explanation. Perhaps we'll discover new physics, modifications to general relativity on cosmic scales, or new properties of dark energy. Or perhaps we'll confirm that our current models are correct, just more complex to apply than we initially thought. By the 2030s, we'll likely have answers to many of these questions. We'll know whether the KBC void is a major challenge to standard cosmology or an interesting, but ultimately minor detail. We'll know whether it explains the Hubble tension or whether that discrepancy points to something else entirely. And we'll know whether voids of this scale are rare flukes or relatively common features of cosmic structure. Until then, we're left with the knowledge that we're floating through an enormous bubble of emptiness, a region of space, perhaps 2 billion light-years across, where galaxies are scarcer than they should be. We're not at the edge of this bubble looking in. We're near its center, surrounded by underdensity in all directions. Every galaxy we see with our telescopes, every cluster we observe, every measurement we make of cosmic expansion is influenced by this fact. The nearest large galaxy clusters, like Virgo and Coma, are at the edges of the void. The great walls and filaments of galaxies, the dense structures that characterize most of the universe, are beyond the void's boundary. Out there, at distances greater than 1 billion light-years, the universe returns to normal density. But here, in our local neighborhood, space is emptier than average. And we have to account for that if we want to understand the universe beyond our local bubble. This is simultaneously humbling and exciting. Humbling because it reveals how our local environment affects our observations in ways we didn't fully appreciate. We thought we were observing from a typical location, measuring properties that applied universally. Now we know we need to be more careful, to correct for local effects before drawing global conclusions. But it's also exciting because it shows that the universe still has secrets to reveal. After decades of galaxy surveys and cosmological measurements, we're still discovering fundamental features of our cosmic neighborhood. We're still refining our understanding of where we are and what that means for our observations. The universe is more complex, more interesting, more full of structure on all scales than we might have guessed. And understanding that structure is one of the great challenges of modern astronomy. Standing on Earth, looking out into the cosmos, we see galaxies scattered through space like cities seen from an airplane at night. Some regions are dense with light, others are dark. We measure distances, track motions, calculate expansion rates. And all the while, we're doing this from inside an enormous bubble of emptiness. The Milky Way, our island of stars, sits in this bubble along with our local group and a scattering of more distant galaxies, stretched thin across incomprehensible distances. Around us, in all directions, extending for 1 billion light-years or more, space is quieter than it should be. Fewer galaxies, less matter, a void in the cosmic web where structure is sparser than the universal average. And then, beyond that edge, the universe returns to its typical state. Filaments of galaxies, rich clusters, the busy cosmic tapestry. We're in the quiet part, the empty part, the part where galaxies are rare and darkness dominates. This is where we've always been, though we're only now beginning to fully realize it. Every observation of distant supernovae, every survey of galaxy positions, every attempt to map cosmic structure has been done from this unusual vantage point. And now we're trying to figure out what that means. How much of what we think we know is universal truth, and how much is shaped by our location? How much does the void affect our measurements, and how do we correct for it? These questions don't have simple answers. They require careful analysis, better data, more sophisticated models. But they're the right questions to ask, and asking them is how we make progress in understanding the universe. The KBC void is a challenge, yes. It complicates our measurements and questions our assumptions. But it's also an opportunity to test our models more rigorously, an opportunity to develop better techniques for extracting universal truths from local observations, an opportunity to understand cosmic structure at its largest scales. The void is teaching us that the universe is more varied, more complex, more interesting than simplified models suggest. That's not a problem to lament, it's a feature to celebrate. Because complexity means there's more to discover, more to understand, more mysteries waiting to be unraveled. And that's what drives science forward. Not the confirmation of what we already know, but the encounter with the unexpected. The KBC Void is unexpected. A structure so vast that we're inside it without having realized it for most of human history. So empty that it affects how we measure the universe's expansion. So significant that it might require us to rethink how we apply the cosmological principle. Yet it's also natural, a consequence of gravity shaping the distribution of matter over billions of years. A feature predicted by our theories, even if larger and more prominent than typical examples. A part of the cosmic landscape that galaxies, including ours, happen to inhabit. We're not special for being here. We're just lucky enough to have developed the technology and understanding to recognize where we are, to map our cosmic neighborhood and realize it's unusual, to see the void and understand its implications. That understanding is an achievement worth celebrating. It took centuries of astronomical observation, decades of galaxy surveys, years of careful analysis. It required telescopes powerful enough to see billions of light years into space. It required computers capable of processing millions of galaxy positions. It required theoretical frameworks sophisticated enough to model cosmic structure formation. And it required scientists willing to question assumptions and follow evidence wherever it leads. The result is the story we've told tonight. A story of discovery that we're in a void, a vast region of space where galaxies are sparse. A story of implication that our measurements of cosmic expansion might be affected by this unusual location. A story of ongoing research as astronomers work to pin down the void's exact properties and determine its significance. And a story that's still being written, with new chapters coming as better data arrives and our understanding deepens. The universe has been around for 13.8 billion years. Humanity has been studying it scientifically for only a few centuries. We've learned an enormous amount in that time, mapped billions of light years, understood cosmic evolution, discovered dark matter and dark energy. But we're still beginners in many ways, still encountering surprises, still refining our understanding. The KBC Void is one of those surprises. It's a reminder that the universe is vast and complex and full of structure we're still cataloging and trying to understand. It's a challenge to our assumptions about measuring the cosmos from our particular vantage point. And it's an invitation to dig deeper, to observe more carefully, to think more rigorously about what our measurements actually tell us. So yes, we're in a void. An enormous, terrifying void that challenges our cosmological measurements and our sense of where we are in the universe. But we're also in a universe that rewards curiosity, that yields its secrets to patient observation and clever analysis. And the fact that we can detect the void, measure it, study it, and begin to understand its implications is a testament to how far we've come. From ancient astronomers who thought the stars were fixed lights on a sphere, to modern cosmologists mapping structure across billions of light years. We've learned to read the cosmos, to take measurements from our small planet and extract truths about the universe as a whole. That's remarkable. And the KBC Void, for all the challenges it presents, is part of that ongoing story of discovery. It's a feature of the universe that we didn't expect, that we're still working to fully understand, that might change how we think about cosmic structure and our place within it. It's where we live, in a void, a bubble of emptiness surrounded by a universe full of galaxies and structure. Not because we're special, but because that's just where the Milky Way happened to form. In a region of the early universe that was slightly less dense than average, that evolved into this enormous underdensity over billions of years. And now, 13.8 billion years after the Big Bang, we're here to notice it, to measure it, to understand it. That's the human story in a cosmic context. We're matter that became aware of matter, structure that evolved the ability to study structure, a tiny part of the universe that can nevertheless comprehend the whole. And even when we discover that our neighborhood is unusual, that our measurements are affected by where we are, we don't give up. We adapt. We refine our methods. We keep pushing forward in our quest to understand. The KBC Void won't stop us from figuring out how the universe works. It's just one more piece of the puzzle, one more factor to account for, one more challenge to overcome. And in overcoming it, in learning to correct for our location and extract universal truths despite being in an unusual place, we'll deepen our understanding even further. That's the nature of science. Every answer raises new questions. Every discovery reveals new complexity. Every observation teaches us something we didn't know before. The void is the latest lesson in that endless curriculum. A structure so large we're inside it, so significant it affects our cosmology, so fascinating it will occupy astronomers for years to come. Thanks for joining me on this journey into the largest void ever found. The universe is vast and strange and full of mysteries. We're privileged to live in a time when we can study it, map it, and begin to understand our place within it, even if that place turns out to be inside an enormous bubble of cosmic emptiness. The void is where we are, but it's not who we are. We're the species that can recognize the void, measure it, understand its implications, and keep exploring despite the challenges it presents. That's what makes us remarkable. Not our location, but our ability to transcend it through observation and reason. To see beyond our local neighborhood and glimpse the universe as it truly is. Complex, structured, vast beyond imagining, and endlessly, wonderfully fascinating. For most of human history, we thought Earth was the center of everything. Then we learned Earth orbits the Sun. Then we learned the Sun is one star among hundreds of billions in a galaxy. Then we learned our galaxy is one among hundreds of billions in the observable universe. Each step was a lesson in cosmic humility. The KBC Void is another such lesson. It's telling us that even our measurements of the universe's most fundamental properties might be skewed by our local environment. That we can't take for granted that what we see nearby reflects what exists everywhere. That the universe is vast and complex and full of structure on scales that dwarf our intuition. Standing on Earth, looking out into the cosmos, we see galaxies scattered through space. We measure their distances, track their motions, calculate how fast the universe is expanding. And all the while, we're doing this from inside a bubble of emptiness so large that light takes billions of years to cross it. The Milky Way, our island of hundreds of billions of stars, sits in this bubble, along with our local group of galaxies and a scattering of more distant galaxies, stretched thin across incomprehensible distances. Around us, in all directions, stretching for 1 billion light years or more, space is emptier than it should be. Fewer galaxies, less matter, a void in the cosmic web. And then, beyond that void's edge, the universe returns to normal density. Filaments of galaxies, rich clusters, the busy cosmic tapestry that characterizes most of space. We're in the quiet part, the empty part, the part where galaxies are sparse and darkness dominates. This is where we've been all along, though we're only now beginning to fully realize it. Every measurement of distant supernovae, every survey of galaxy positions, every attempt to map cosmic structure has been done from this unusual vantage point. And now we have to figure out what that means. How much of what we think we know is universal truth, and how much is local circumstance? How much does the void affect our observations, and how do we correct for it? These questions don't have easy answers. They require more data, better models, careful analysis. But they're the right questions to ask. And asking them is how we make progress. The universe doesn't care whether we find it convenient or inconvenient that we're in a void. It doesn't adjust its structure to make our measurements easier. It is what it is, and our job as scientists is to figure out what that is, despite the challenges. The KBC void is one of those challenges. A feature of cosmic structure so large that it affects how we perceive the universe. An emptiness so vast that it shapes the observations we make and the conclusions we draw. It's humbling to realize that our cosmic address includes not just a planet, a star, and a galaxy, but also a void. A 2 billion light-year bubble of underdensity that we float through, surrounded by darkness and distance. But it's also exciting, because recognizing this fact opens up new avenues of research, new questions to answer, new ways to test our understanding. The void is not a dead end, it's a starting point. A clue that the universe's structure on the largest scales is more complex and more interesting than we might have guessed. And understanding that structure, mapping it, explaining it, is one of the great projects of 21st century cosmology. So yes, we're in a void. An enormous, terrifying void that challenges our assumptions and complicates our measurements. But we're also in a universe that rewards curiosity, that yields its secrets to patient observation and clever analysis. And the fact that we can detect the void, measure it, study it, and begin to understand its implications is a testament to how far we've come. From ancient astronomers who thought the stars were fixed lights on a sphere, to modern cosmologists mapping structure across billions of light years, we've learned to read the cosmos. We've learned to take measurements from our small rock orbiting an average star in an ordinary galaxy floating through a void, and from those measurements, extract truths about the universe as a whole. That's remarkable. And the KBC void, for all the challenges it presents, is part of that ongoing story of discovery. It's a reminder that the universe still has surprises, still has features we didn't predict, still has the power to make us question our assumptions. And that's what makes cosmology endlessly fascinating. Every answer raises new questions. Every measurement reveals new complexity. Every survey of the sky shows us something we didn't expect. The void is the latest chapter in that story. A structure so large, we're inside it without having fully realized it until recently. An emptiness so profound that it might be affecting every measurement we make of cosmic expansion. A challenge to the cosmological principle, or at least to how we apply it. And a reminder that our place in the universe, while not cosmically privileged or special, is also not as typical or average as we might have assumed. We're in a void. A vast, dark, empty region of space where galaxies are scarce and distances are enormous. It's where we've always been, though we're only now seeing it clearly. And it's where we'll remain, at least until the expansion of space carries the Milky Way to the void's edge billions of years from now. By then, the universe will have changed in ways we can barely imagine. New galaxies will have formed, old ones will have merged, Stars will have lived and gone, and the cosmic web will have evolved. But the void will still be here, though perhaps grown larger or merged with neighboring voids as cosmic expansion continues. And if there are still beings looking out at the cosmos from some planet in some galaxy, they'll face the same challenge we face now, trying to understand the universe from a single vantage point, trying to separate local effects from universal truth, trying to see the whole when they can only observe a part. That's the nature of cosmology. It's science done on the grandest possible scale, using observations of the most distant objects we can detect to draw conclusions about space and time and matter and energy. And sometimes we discover that our local cosmic neighborhood is strange in ways we didn't anticipate. The KBC void is one of those discoveries. Terrifying in its implications for our measurements and models, humbling in what it reveals about our cosmic address, but ultimately exciting in what it tells us about the universe's complexity and our ability to unravel that complexity through observation and reason. We're in a void, but we're not lost. We know where we are, we know what it means, and we're working to figure out how to account for it. That's progress. That's science. And that's why, despite the challenges, despite the uncertainties, despite the uncomfortable realization that we're in a very unusual place, cosmology continues to move forward. One measurement, one survey, one discovery at a time. Thanks for joining me on this journey into the largest void ever found. The universe is vast and strange and full of surprises, and we're privileged to live in a time when we can study it, map it, and begin to understand our place within it. Even if that place turns out to be inside an enormous bubble of cosmic emptiness.